Hi guys, this is your calc tutor back again, and in the last video we talked about some very basic applications of integrals, namely to the area between curves, and this video we're going to be talking about applying integrals to find volumes. Okay, so let's get started. Um, yeah, so this is a concept that you should be familiar with, right? Like this is just a refresher. So the integral of any function is going to give you the area under the curve, right? And you can think of it as adding up these infinitesimally small rectangles underneath the curve to find the total area, right? But today we're going to be talking about going one step further, that is integrating area, cross-sectional area, to be specific, to find volume, right? So what does that look like? And the answer is this, right? So say this is your function, and you know that your cross sections are going to be squares, and they're going to have their base on the function, right? So their bases are on the function, so this is your f of x, and it's going to be a square cross section. And you can divide this, so say this is one whole solid, basically, right? I'm not exactly the best drawer out there, but this is one whole solid. And essentially, you can think of this as taking, instead of rectangles, now you're doing rectangular prisms, right? So if you look at one of these rectangular prisms, this is what it looks like, right? This is your width dx. You know this is f of x, and then the height is also f of x because you know it's a square, right? So if you wanted to find the total volume, all you would do is sum up your whatever n number of rectangular prisms, and then your volume would be length times width times depth, right? So f of x squared times dx. And obviously, since we want to get as exact as possible, we're taking the limit as n approaches infinity, which also means dx is approaching 0. And what is this? This is nothing but the integral of f of x squared dx, right? So in this way, we can transform this expression for cross-sectional area into the volume of the surface. And it's not just simply a square thing. You can also do it with, say you have a rectangle, right? Instead of square cross sections, now you have a rectangle. And say you have, once again, f of x is going to be your base, right? Because let's redraw that image. This is going to be your base, and then your rectangle is going to be quite a bit longer, right? So let's say the height is k of x, or k, I'm sorry, k times longer than the base, right? K times f of x. Once again, you're going to have this tiny little width dx that you're going to limit to 0, right? Which is going to turn this sum of rectangles. So you'd have the sum of length times width times depth. You turn this into basically an integral, once again, of kf of x squared dx. Say you want to have an isosceles triangle, right? I'm really coming up with something random here, but an isosceles triangle such that the base is, of course, f of x, and then your depth is going to be dx, as always. So the base is f of x, and let's say the height, or let's say these other two sides are now going to be, um, say like 1/2 f of x, right? Obviously, this is not to scale, but, or actually, you know what? Let's not even give it in terms of the sides. Let's say the height is 1/2 f of x, right? Obviously, this isn't to scale, but the same process applies, right? You're summing up these infinite little slices, okay? And you're making the slices thinner and thinner, and you get now you have a triangle. So instead of length times width times depth, it would be depth, so your dx times base times height over 2, right? Because that's the area of a triangle. So you'd have 1 half f of x squared over 2, or 1/4 the integral of f of x squared dx, right? So in this way, you can transform these cross-sectional area formulas into actual volumes, okay? Now let's look at an example here. So, the base of a solid formed by cross-sections is the region between root x and 1/2 x. Cross-sections perpendicular to the x-axis are squares. Find the total volume. Should have put total in there. So the way we attack this problem is pretty simple, right? Let's start by drawing one of our cross sections, okay? So it's saying perpendicular to the x-axis. So this is the x-axis, this is the y-axis. So perpendicular to the x-axis would be going up this way. So our cross section might look something like this, and it would be a square, right? And imagine this is coming out towards you. And so the base of this square is going to be f of x, right? Which is, so this is f of x, which is in this case the distance between root x and 1/2 x. And since it's a square, this is also going to be f of x, right? And technically there's always this infinitesimal width dx, but I'm going to omit it for now because I'm just going to skip that step entirely. So now we'd have the integral of f of x squared, right? Because this is the cross-sectional area. And we're integrating, once again, integrating area with respect to x to get volume, right? So the integral of f of x squared dx is going to give you your volume. And in this case, what is f of x? You'd have root x minus 1/2 x squared dx. And let's find out our bounds. So our lower bound is 0. Our upper bound is where the two graphs intersect. So you'd have x equals 4. So 0 to 4. And you can plug this into your calculator or you can evaluate it by hand. I'm not going to do that right now for the sake of time, but essentially this is how you would set it up. Okay? Now let's say you wanted your cross sections perpendicular to the y-axis to be squares instead, right? And instead of squares, let's go rectangles. And we'll say that height is 3 times base. Okay? So, what are these going to look like now? So, it's definitely not going to look like this square. Oh, whoops. Sorry about that. I'm trying to delete this. Yeah. So, it's definitely not going to look like a square, right? Now they're perpendicular to the y-axis, so they're going to be going this way, right? So, our cross sections are going to look something like this. And once again, imagine this is coming out towards you, right? Your rectangle is going to look something like this. And it's not the best artistic rendition, but yeah, you get the point. So this is going to be your rectangle, right? The base is f of y, and the height is 3 times f of y, and the width is dx, right? Now, since we're in the y domain, perpendicular to the y-axis, we need to convert these functions into functions of y, right? So you have y equals root x, square both sides, you get x equals y squared. So that's our first one. And then y equals 1/2 x, x equals 2y. That's our second one, right? And obviously, this is going to be right minus left, right? The region between the two curves when you're dealing with y is always right minus left. So in this case, our right is going to be our x equals to y, and our left is going to be x equals y squared. So this means f of y becomes or 2y minus y squared, okay? And when we write down this integral, we're going to go from 0 to our intersection point. Before, we had it as x equals 4. So at x equals 4, we know that y is going to be 2, right? So 0 to 2, since we're in the y domain, and we'd have, this is, the area of this cross section is 3f of y squared. So you'd have 3 times f of y, 2y minus y squared dy. And it's as simple as that. It all depends on what like type of cross sections they give you, right? And yeah, that's basically it.